Now we go to two-player game. So you have two people. One is you, and the other guy is, I always will use a probability god or nature. So what the heck is this? You are doing this. You have T round. You can think of this as T day, day 1, day 2, day 3, day 4, day T. And let me recap. I can write this symbol, means 1, 2, 3, 4, 5 up to T. Okay. So you have a for loop for 1, 2, 3, 4, 5 up to T. So what does it mean? It means day 1 you do this, day 2 you do this, day 3 you do this until day T. So first, at day T, you do something called your action at day T. Okay, this is an abstract algorithm. And once you do your action in day T, what happened to the nature or player 2? You can think of nature do something to you. This can be anything nature do. Okay, and then number 4. So now you have two things. The first is your action. So you will put your action inside a function called loss. And then this function is what you do and what nature do. So this is a loss. So how much you lost is how much nature gains. So this is now game theory. It means what you want to do is minimize how much you lost, and what nature do is maximize how nature gain. Usually these two functions are opposite to each other. Okay, so that's the game theory basic setting. And we focus on our perspective or your perspective, so we don't care player 2. So how nature gain, we don't care. So we can ignore it. So I don't need to have this line anymore. So now I only have this. And I also change my wording. I don't care about nature. So I will say, I do action. I see nature give me something. I suffer something. So this is now all on your perspective. So I have this. This will be the basic game theory framework. We don't care about player 2. We just care about player 1. So this is the basic setup. So now, after all the basic notation, convex optimization and player game, we can now start the meat. This part will be very long. So I'm going to minimize something random. What's random? I have this. This is a random variable. So this thing follow a distribution D. So naturally, I will have this. First, I didn't say anything about D. It's possible that we know what is D. And it's also possible that we don't know what is D. Not our focus. Now, if we know the distribution D, then this can be called parametric, because D have some parameter, then it can be parametric distribution. If we actually don't know what is D, then that means we don't have parameter on D. Then it can be aparametric, or we can say we learn D by data, then that will relate to data induced or data dependent randomness. Okay, so these are not important. But my point is, now we want to minimize something on random. And here's the thing, h is a function on random variable. We just say that if this is a random variable, h on a random variable is also a random variable. So therefore, minimizing a random variable does not make sense. Why? Because randomness is controlled by probability god. So probability god control randomness, which is not you. You have no choice on controlling randomness. So technically speaking, this thing does not make sense. What will make sense is this. So what the heck is this? Now, this h is not just randomness, but also an x. This is what we can control. So player now can control x. So this will be the basic stochastic optimization framework. So what does it mean? You need to know the meaning. It means I have a h. This h has two parts. This is the player 1, can play this. This is the player 2, can play this. Player 1 cannot control this. Player 2 cannot control this. So they only control half of the story. Player 1 wants this as small as possible. Player 2 wants this as big as possible. And they are fighting each other. And player 1's choice is minimize this on x inside a region. I call it big X. Player 2 choice is very simple. Maximize this on this thing inside a set that, okay, I don't know how to draw it, but let's say this is a set. So they are like enemy of each other. Okay, and actually I make a mistake because this is a set, so it means D. Okay, so now this is the game theory, mixing up with optimization, mixing up with this stochasticity. So now here is a very crazy slide. We have a random variable, and then inside distribution D, and this function is taking the random variable to R, and actually this is wrong notation because also X. Okay, there's also X. So I have this, and now this is still a random variable. So actually it's still not making sense. So this is what I mean from the very beginning. Let me recap. I have this thing, right? So actually I want to minimize another f on top of this h so that something is small. And this f now have so many types. and all of them are the f. So therefore, this is all the f on top of the h. Okay, so for example, you have the average case. So what the heck is average case? So average case means f of the h is e of the h. So I have this. So it has a meaning, right? It means on average of the randomness, how small can h be? This is another one. This f of h is the worst case of h. So it's like the max of h. So this is the f. This means what? Among all possible randomness on this random thing, I select the largest way it can go up the h. Now for this whole thing, how small can it be? Okay, you see the meaning are different. And then now here's more crazy stuff. Okay, the thing below are not important, but just for you to get a big picture, so I talk about them. You have something called control conditional value at risk. So it's saying this is my f of a h. So CVAR is something related to risk. So I will talk about it soon. So you can figure out as a f for a moment. I will talk about it soon. And then you can have quantile. That means what? I have a h. Now I have another f. And this f is what? I measure an alpha quantile. So 25% quantile, 75% quantile. And if alpha is 0.5, that means 50% quantile, then this is median. Okay? So what the heck is this two? It's like this. I have a function, h. This is a random variable, right? So let's say this random variable is a Gaussian random variable. Then median is here, right? But now let's say my random variable is not Gaussian. My random variable looks like this, okay? Looks like this. The distribution looks like this. Then my median may be like this. And then this is median, okay? And then this is like 75 percentile. Then what the heck is this guy? This guy is saying, please minimize the location of my 75 percentile on average. Then what the heck is this guy? This guy just saying, please minimize the average. So you can see in statistics, you can have average and you can have median or quartile. So basically you can think of this as different way you measure the statistic. What about the max? It's like, okay, please give me the worst one. Something like that. So these are all related. So these are all like statistical measure. Now, lastly, you have two more that is very interesting. The first one is chance. Now you see I minimize nothing. Yeah, first of all, you can have minimize a zero function and then you subject to x smaller than x. So this means please find any small x inside this big X. And now my big X is not arbitrary. It is saying the probability that my h is smaller than a number is at least as this. So think about, let's say epsilon is 0.01, then 1 minus epsilon is 0.999. So what the heck is it saying? Then this is saying the probability on the randomness of my h is smaller than, let's say 5, this is a tau, is 99.9% chance. So this is saying please find a x such that the chance of h is smaller than 5 is 99.9% probability. So this is another way you can have the f. And since you are talking about the probability, so that's why here is nothing. It's 0. And then lastly, you have something called entropic regularization. Is you still have this part is the same, but now you add something like this. This relates to how aggressive you are on taking extreme value. I'll talk about it soon. So now I'm going to talk about it one by one. And this will give you the big picture of what is random optimization. So the basic two is the average case and the worst case. So what's average case? You just have an h that have two parts. The x, that means player 1 control. The second part is the random part, that means the player 2 control. And you are saying, because this whole thing is random, I just look at on average, how does it behave? So basically is what? You focus on minimizing the average. What is average? From statistics, you know an event have a distribution like this. That means you focus most likely here. You don't care about the extreme case. So this means you ignore extreme case. Extreme case means tail. So I mean this is a tail, this is a tail. Okay, so basically you are saying, I just care about the average. I don't care about extreme case. So this is the first way you can think about. Then what about this one? Well, this actually is the opposite. You care about the extreme case. You are saying you are very conservative. in the probability thing, you always think about the worst case. So you want to make sure the worst case is not so bad. So this is the opposite. And if you look at the math, what does it mean? It means among all the randomness, I don't care all the average guy. I care about the special random guy that make my H as big as possible. And I'm looking at a particular random guy that make it the biggest. After I consider the worst possible case, I minimize this worst possible case. So on top is like on average behavior. On top is like the worst case behavior. So these two are the different meaning. And this is statistic, right? But you can link it back to a vector norm. So if you have a vector, let me go back to the beginning. You have a vector. This is a vector. The L2 norm is how big is this radius. The L infinity norm is how big is this two thing, which is this is the longest one. So the average case you can think of it is the L2 norm. That means it's the ball like this. The worst case is the L infinity norm. That means you care about the worst case because now you have two-dimension case, you have two things. This one is shorter, this one is longer, so you care about the worst one. That means the longest one. So this is the two case. Then what the heck is this two case related to this one? This is the idea. CVAR is between the average and the worst. So you can think of average and worst inside a set as this set is the what? This set is the statistical space. Okay, I just make up some name. Now you have an average case here and you have a worst case here. And in between this part is how much you are on average and how much you're on the worst. And this whole thing is the CVAR. So what is CVAR? This is informal. The full expression is this math. You don't need to know the math too much. So it means this part means what? This is average of H, right? So average of H looks like this, right? But now you are saying, I'm not talking about all the H. I only talk about the H that is larger than a quarter. So suppose alpha is 75. That means I only look at the highest 75 percentile of my H. And I look at this on average. So this is looks like 75 percentile above average. Something like that. So this is the CVAR. So if you understand this part, and you think of alpha is a number between 0 and 1 that control how average you want, how worse you want, then you know what the heck is CVAR. So basically it's this 2K in between. Okay? And then for CVAR, if alpha is 50%, then you get median. And if you general alpha and you don't take average, then this is a particular percentile. 25 percentile, 75 percentile, whatever, right? Okay, these are just this. So they are all related to the CVAR. And for the median, this can think of as the L1 norm. So therefore, this is L2 norm, this is L infinity norm, this is L1 norm, this is convex combination between L2 norm and L infinity norm. This is like an abstract thinking. Okay, and we will focus on this too, don't worry. And I just give you this example and tell you their interrelationship because you can have a bigger picture. Lastly, we have two more. Is chance constraint and entropic. What the heck? Chance constraint means what? You don't care about this. You don't care about the exact output. You just say, I want the probability of something occur, then I'm happy. So what does this mean? This means I have an H. Suppose tau is 5. So here's the thing. I can have value 1, I can have value 2, I can have value 3, I have value 4, right? And so on, right? And actually I can keep going on. Let's say I can have value 100. So I have 100 number. And I only want this 4 number. So the probability will be whole thing divide, this is the event I can have, right? So this thing divided by this thing is the probability, right? So I'm saying, please find a small h such that among all possible outcome of h, smaller than a number tau I define, and this probability is as big as possible. And this is totally different from what I do previously. Previously is, I have h, I can take any value. Now I'm saying find an x that give me the smallest value under some condition, on average, on extreme case. Now this is chance is like, I can take many value, I don't care, all of these are okay. Please give me the x such that I randomly choose value among here, it go to this region with a 95% probability. So now you can see this suddenly give you a total different story, and this is called chance constraint. Okay, that means what? This is about probability. Okay, and this also is related to average and worst because it's somehow in between probabilistically. Okay, and lastly, we have the entropic. So what's the entropic? So entropy, okay, suppose you don't know, entropy is P log P negative. So what the heck is that? This is information theory, which no time to explain what the heck is. Basically, it's like this. I mean this thing, right? So I mean this thing and I mean this thing. If I mean this thing, I minimize the green. So my green is small, but there's a negative sign. This thing is small means what? Means without the sign is big, right? Because there's a negative sign. So low, this term means the P log P, which is high entropy. So I actually make a mistake. Low negative entropy means high without negative entropy. And P log P is high. There's a graph saying P log P is high exactly at this point. It means distribution spread out, more uniform. So this is more related to categorical distribution. So that is, you have some probabilistic event. Suppose you have option 1, 2, 3, 4. So if your probability of choosing one is very high, that means your PDF, your probability distribution function should look like this. It means the probability you are here is very high, probability is very low, very low, very low. This actually has low entropy. What does high entropy mean? High entropy means your probability looks like this. You even out. So it's like event 1 have 25% chance, event 2 have 25% chance, event 3 have 25% chance, and event 4 have 25% chance. So high entropy means it's more evenly distribution, more uniform. So it means you can take everything. So this is the idea of entropic regularization. So if you minimize something related to entropy, so it means you are encouraged to be more diverse. Because I have 4 options and you want all of them. And classical statistical is saying I have 1, 2, 3, 4. Please give me the one with the highest probability and ignore the rest. And entropic is saying please don't focus on one option, do more. So that's the meaning. Okay. And because the classical have no entropy, so you can think of classical is like more greedy. And then entropy is like more willing to explore alternative strategy. So that's the meaning. So you have a number lambda to tell you how willing you want to explore alternative strategy. Okay, so that's the entropic. So basically that's everything in stochastic optimization. So let me recap. So basically you have how you measure the output of an H. Basically in how you consider risk. You can consider average risk, the worst risk, CVAR risk, which is a funny risk, quantile risk, median risk, probability risk, and how willing you explore alternative option risk. So these are all stochastic optimization. And of course, we only care about these two. Okay, we only care about these two because no time to talk about all the other things.